Holz-Brucke Bridge Stress Analysis, presented by Zachary Andrews, Zachary Malash, and Akil Nagash. Affiliation, Mechanical Engineering, Kettering University. The Holz-Brucke Bridge is considered one of the last wooden-covered bridges. The build contract was signed on a yellow line paper and a handshake. Construction began in 1977 and nearly took 2 years to complete. It was opened in 1980 and formally dedicated on September 9th of the same year. Being a wooden-covered bridge, the Holz-Brucke used exactly 163,288 board feet of wood, 100,000 of which were shipped directly to Frankenmuth to be air-dried, and 25,000 were to be fashioned as rafters and were delivered from New Hampshire in a 1955 Ford pickup. Moving the bridge proved to be difficult, for the bridge was pulled by two twin red and white Holstein oxen aged 4 years old. Bright and Buck pulled the bridge along a track made with oak rollers over a 12-day span at a max speed of 3 inches per minute. The Holz-Brucke Bridge ended up costing approximately $1.1 million to build before another $317,000 were spent in 2015 to remodel it.
We started our analysis with a list of known values coming from various websites, including the owners of the bridge. We found the values for the length, overall width, ultimate values of shear and tensile strength of Douglas fir, dry weight of the bridge, and general information of an EV Hummer. We then assumed a material of uniform Douglas fir, the bridge cross-section to be a rectangle, and the overall structure to be a height of 0.41 meters. Using this information, we generated distributed loads over the length of the bridge for pedestrians, vehicles, and the bridge.
After the assumptions and simplifications are made, we start our calculations with a static analysis. Using equations of equilibrium, we find AX and AY forces. Since the body of the bridge is assumed to have a uniform structure and a uniform distributed load, we know that the forces AY and CY are equal. With this information, we find AY equal to the weight times the length over 2. Once we have AY, we are able to find the equations for shear force and moment. By taking a cut at X length along the bridge, again using the equations of equilibrium, we can find the expressions for shear force and moment. Using the expressions for shear force and moment, we then find the maximums of each. The max of shear is located at either end of the length AC of the bridge, while the maximum of the moment is located at the midpoint of length AC along the bridge. Next, we move to our mechanics and material stress calculations. Using the equations for shear and tensile stress from bending, and substituting our expressions for shear force and moment, we are able to find the respective stresses at any point along the length AC. Using our max shear force and moment in the equations of stresses, we are able to find the max shear and max tensile stress. Moving to the final analysis, we generate expressions for the factor of safety in both shear and tensile. Using a similar substitution as before, we plug in the expressions for shear and tensile stresses. Using the maximum of the stresses, we can find the most critical points for the safety factor. The safety factor of tensile is at greatest concern of 1.62, and the factor of safety of shear is of little concern at 95.15.
Starting at statics and moving our way through mechanics of materials, we construct several nested functions, each being used for the next tier of structure and stress analysis. Using our general assumptions on the uniform composition, column spacing, and density of people and vehicles, we develop the factor of safety for the bridge under the maximum load of 24 EV Hummers and 602 people. Our calculated factor of safety for tensile stress is 1.62. The safety factor, while not at the point of failure, is something to be very alert to, as it is relatively close to it, at a safety value of 1. While the factor of safety of shear stress is very safe with a calculated value of 95.15. Overall, while the bridge nears the point of failure, under this load, it is structurally sound.